Hi, this is Kan-Lin speaking. I'm from the Department of Energy Engineering, National United University. In this unit, I'm going to talk about the Butler-Volmer equation. This Butler-Volmer equation is we assume the electrode is on the smooth surface, that anything happen is a simple single electron transfer, the electrochemical reaction. In the previous section or the unit will be mentioned, the electrode structure of the fuel cell is more complicated. There's a multiple layer, and each layer had a different kind of properties. But over here, we only consider a very smooth single-phased solid electrode, and the reaction is taking place at the electrode surface. Let's consider a simple electrochemical reaction, a redox reaction. This reaction only taking place inside the solution, and only the ion, the valence of the ion change. That means, for instance, oxidizing species accept the electron and become the reducing species, or the reducing species lose electron and become the oxidizing species. This is a reversible reaction. Example like a cupric ion, like a copper 2+, it can be reduced into the cuprous ion, copper 1+ ion, or the ferric ion can be reduced to ferrous ion, or the ferrous ion can be oxidized into ferric ion. This ion all dissolve into the aqueous solution, and the reaction taking place at the electrode and the solution interface. It's simply just one electron transfer. We don't consider anything else. So over here we define the forward reaction is in this direction, and the backward reaction is a reverse the reaction, so over the other direction. In this case, the forward reaction is a reduction reaction, and the backward reaction, the direction is a oxidation reaction. So we can write the net electrochemical reaction rate as equal to the forward reaction, the rate constant times the oxidizing species. For instance, this is a forward reaction, and depends on the concentration of oxidizing species, and the time the rate constant, the forward rate constant, minus the backward reaction rate. The backward reaction rate equal to the rate concentration of the reducing species times the backward reaction rate constant. In this, we assumed the reaction is a first order respect to the reactant concentration. So that in reality they maybe have the different reaction order here. So over here, the rate, they are the Kf or Kb are the rate constant for the forward or the backward reaction, and then the COX is the oxidizing concentration, and then CRD is a reducing species concentration, and this is the reaction flux of the reactant. That means the reaction rate, net reaction rate. Because this one only taking place at the electrode surface, so we had to divide it by unit surface area over here. So the electrode surface get bigger, then the total reaction rate will be equal to this times the reaction electrode surface area over here. And this reaction rate is mole per second per centimeter square. But in the electrochemical reaction, we like to express the reaction rate as the current density. This can be done through the Faraday law. Over here we use Faraday law, so we can convert the electrochemical reaction rate into the current density here. The definition for each item is like this. The I is a current density, is amp per centimeter square. The amp is a coulomb per second here. The N is the number of electron transfer. That means 1 mole of the cupric ion reduced to cuprous ion. It might involve 1 mole of electron. Or the ferric ion reduced into ferrous ion is also involve 1 mole of electron. So the N equal to 1. And the Faraday constant is mean the 1 mole of electron, how much charge it possessed. So N times F actually means 1 mole of the ion being reduced or oxidized, how many charge had been passed through. So this is the reaction rate per unit of electrode surface area, how fast the reactant was consumed or the ion was oxidized or reduced. So NF times J over here, the more and more cancel out each other. The coulomb per second per centimeter square become this one. And the coulomb per second, that's M, let's give you the current density. So based on the Faraday law, we can express the electrochemical reaction rate into the current density. And the current density, the positive current density I greater than 0, that means the forward reaction rate is greater than the backward reaction rate. That means the net reaction will be the oxidation. When the I is negative, less than 0, that means the backward reaction rate is faster than the forward reaction rate. The net reaction will be the reduction. So the sign of the current density just described means the direction of the reaction. Now let's try to express the current density as a function of electrode potential. How the electrode potential will be affected on the reaction rate or the current density. We can introduce the Arrhenius equation because the rate constant can be expressed as a function of the activation energy over here. This Arrhenius equation, that's usually in the general chemistry, it's been described that way. And so the forward reaction, the rate constant, we can express as the rate frequency constant times the forward activation energy over here. And also the backward rate constant we can also express as a function of the backward activation energy over here. So this concept, the activation energy, you might think this oxidizing species, the forward reaction oxidizing species, have to overcome this delta GF, the forward activation energy, in order to climb through the energy barrier and go to the reducing species. The forward reaction had to overcome the delta GF. And for backward reaction, the reducing species had to overcome the delta GB, this energy barrier, to go through and then become oxidizing species. So the greater the energy barrier, the more difficult the reaction will go through. When you change the electrode potential, we attribute the electrode potential will be changed the landscape of this potential barrier over here, and that means change the delta GF and the delta GB. Following slides will give an example how the electrode potential will affect on the activation energy. We simplify this, say at the equivalent potential phi 0. That means there's no net reaction. The forward reaction equal to the backward reaction. So over here we assume that delta GF at equilibrium equal to delta GB equilibrium at this condition. So the forward reaction is equal to the backward reaction, the net reaction rate is 0. That means the reaction is at equilibrium. When the electrode potential phi 0 changed from phi 0 to phi 1, then the energy profile was changed to phi 1. So it's from the original energy barrier changed to the new energy profile. The delta GF reduced, delta GB may be increased. So in this case, it will favor the forward reaction, and then it's not favor to the backward reaction. So the forward reaction will be greater than the backward reaction. The net reaction will be the oxidation, the reduction, the forward reaction. When the electrode potential changes to phi 2, the reverse condition, if this is a reversible reaction, then the delta GB will be reduced from original delta GB0 into the delta GB, and then delta GF will be changed from original delta GF0 to delta GF. Then that will be favor to the backward reaction, so the net reaction will be the backward reaction rate. By using this concept, so the activation energy we can express as a function of electrode potential over here, and this is the fraction. That means if we apply electrode potential on the electrode, how much of the electric energy was attributed to the forward reaction, and how much percentage of the electrode potential energy was attributed to change the backward reaction activation energy over here. So 100% of the electric energy applied on the electrode, only a portion of that will be affected on the forward reaction, and the other portion will be affected on the backward reaction. So this means the phi F plus alpha F plus alpha B equal to 1. The total energy is F times phi over here. With this in mind, then we can relate the current density as a function of electron. Let's go to the next slide. You can see that. So this for the reaction rate over here, the rate constant over here, forward and backward reaction, we can express by using Arrhenius equation, and then the free energy or the activation energy will depends on the electrode potential. So we substitute this into this equation, then it will come out like this. This will indicate that the current density will be function of electrode potential. This equation we can reduce by combined, because this is at an equilibrium condition. This is a constant. It's independent electrode potential. So we can combine this term and then this one into a new constant, and this term make it as a new constant. Then we become like this. So over here we use this K0F equal to K0F plus times exponential minus this term over here into a new constant, then can be simplified like this. So this I equal to NF times K0F, this term, and then minus alpha F phi over RT over here, and the COX minus K0B over here, and then times minus the alpha B F phi over here. So in this one we take a shortcut. So the KF equal to this, if we substitute this KF equal to this one, then we end with this equation. This we may call the Butler-Volmer equation. It's describe a single electron transfer reaction, and is a reversible over here. Consider a forward reaction and a backward reaction. Previous equation we can further simplify it into I0 and then make it like this equation. The only term is electrode potential over here, but over here is the over potential. This means electrode potential minus the potential at the equivalent over here, phi r. And the other term will be lumped into the I0. We call this exchanging current density. So this this equation had two parameters. One is I0. We call the exchanging current density. And the other is alpha F and alpha B. We call the charge transfer coefficient. This can be achieved by assume in the previous equation, if we assumed at the equivalent potential phi r, the current equal to 0, the forward reaction equal to backward reaction. If you can put the phi r into previous equation, and then the forward reaction term becomes this one, and the backward reaction term becomes this one. You try it. I would suggest you can try it. Substitute the phi r into previous equation. The forward reaction becomes this term. And this one, we assume the one-way reaction rate, we let it express as I0, the exchanging current density. Because at the equivalent potential, the forward reaction rate equal to the backward reaction rate over here. This is the exchanging current density over here. So with this, you substitute, then the Butler-Volmer equation can be further simplified into this equation, and the exchanging current density and the charge transfer coefficient will be two major parameters over here. The physical significance of these two is the I0 actually relate to the concentration of the reactant. And over here, I didn't put it in. Also, the true surface area of the electrode. If the electrode is smooth, then the I0 will become very small. If this electrode is porous, made of nanoparticles, then the I0 become very big. It's because over here the area is the apparent area. The true surface area per centimeter square is much higher if we use a porous nanoparticle made of this electron. And the alpha F or alpha B, the charge transfer coefficient, is directly related to the type of catalyst we use or reaction mechanism, because as we mentioned, this one will be affected on the free energy or the activation energy. The activation energy from the chemical sense, it will be affected on the reaction path. So if you change the catalyst or reaction mechanism change, then the alpha will change. So from here we summarize, found the reaction rate simple, the redox reaction, consider reduction and oxidation, simple reduction oxidation reaction. By substitute this Arrhenius equation, and also consider the electrode potential will be affected on the free energy over here in the Arrhenius equation. Then we can simplify this into we call the Butler-Volmer equation. Over here, there's two parameters, exchanging current density and the charge transfer coefficient over here. This one associated with the reaction path or the type of catalyst or reaction mechanism, and this mainly is for the reaction concentration or the area of the electrode. Let's see how the behavior of the current density as a function of electrode potential. Here, we plotted this BV equation into over here. We plot the current density as a function of electrode over potential over here, phi minus phi r over here. So over here there's a two turn here, the forward reaction and the backward reaction. So the forward reaction over here is a reduction. We use a green curve to express the forward reaction, and the backward reaction is a blue over here. Then you can see at a negative electron over potential over here, if this is negative times the negative term, this become very positive. So this term become very significant, and this term become negligible. At a very positive electron potential over potential, this is positive here. Then this one becomes negligible here, and this one becomes significant. So the overall, the electron current as a function of over potential is like S shape, like this. This is the behavior of the Butler-Volmer equation. In the actually over here, in the higher over potential turn here, the opposite turn can be neglected, and in the middle, both had to be considered. Is kind of like linear relationship here.